Hello, I'm Sarita Arve, and with Muhammad Husefa, I welcome you to our presentation on ELLIXR, an open source testbed to democratize extended reality research, development, and benchmarking. This is work we've done with a large team of students at the University of Illinois. Extended reality, or XR, which includes virtual, augmented, or mixed reality, will be the next major computing interface. XR has the potential to transform all human activities, including science, medicine, education, and more. However, there are many challenges to overcome before we can achieve the full potential of XR. There is an orders of magnitude gap in power, performance, and quality of experience between the systems we have today and the systems we desire. For example, for full immersion, we would like about 200 megapixels resolution, but current state-of-the-art delivers about 4. To wear AR glasses all day, everywhere, power needs to be in the hundreds of milliwatt range versus the 10-watt range state-of-the-art today. And there are similar large gaps in other metrics. As we see the end of Moore's law, achieving such improvements would be challenging for any domain. XR comes with additional challenges. First, designing an XR system requires diverse expertise, including in graphics, vision, audio, video, optics, haptics, and more. Second, to get the performance benefits we need, we cannot rely on just one layer of the system stack. We will need cross-layer system optimizations where we co-design the hardware, the compiler, the OS, and the wide range of algorithms for a complete XR system. Third, metrics to measure the goodness of an XR system are complex and still a subject of research. XR requires multiple user-driven end-to-end quality of experience metrics such as motion to photon latency, image quality, audio quality, and more. And finally, today XR is dominated by a few participants with closed proprietary systems. There are no reference systems or benchmarks to jumpstart XR systems research. In other words, there is a large barrier to entry for open R&D in XR systems. So we asked the question, how can we democratize XR systems research, development, and benchmarking so that a broader community can participate to address the challenges to move this field forward? And in this talk, we will describe how we propose to address this question. We have recently released ILLIXR, the Illinois Extended Reality Testbed, to advance the field. ILLIXR has state-of-the-art XR components connected with a modular and extensible runtime system. It is compatible with OpenXR, a recent standard that provides an open interface between XR applications and the system. ILLIXR also supports several quality of experience metrics. It runs on desktop and embedded systems. We have performed an extensive characterization of ILLIXR to identify the performance, power, and quality bottlenecks in XR systems, and we are using ILLIXR in a large number of research projects. So here is a brief demo of ILLIXR. In this window here, we have a user walking around in a physical space, and we see the view from his camera. The window here shows a third-party view of the virtual space that the user is navigating. So here is the position of the headset in the virtual room as determined by ILLIXR. And this third-party view helps us debug our system. Here are the eye buffers that ILLIXR outputs for the user to see. So this is the actual output of ILLIXR. This is a window here to provide a range of information to help understand and debug the system. Hopefully on your screens you can see that ILLIXR is able to provide a smooth experience with good tracking. However, this demo is running on a beefy desktop with a high-end NVIDIA GPU taking lots of power. On a weaker, lower power system, the experience is not so good even for this simple application. So while ILLIXR is a great testbed, there is still a lot to be done. So while we continue to improve ELLIXR both as an open testbed for the community and for our own research, we realized that we cannot do this alone. And so we have formed a consortium with several industry and academic partners, including ARM, Facebook, Micron, Northstar, and NVIDIA, and others. We have three goals with the consortium. First, we would like to evolve ELLIXR into a reference open source testbed that can be used for a wide range of research, development, and benchmarking. To do this, we would like to generate consensus on the components and the interfaces to those components, a modular and extensible runtime, and provide extensive telemetry. We believe ELLIXR provides a solid foundation for this, but a lot more work is to be done that we would like to do with the broader community. We would also like to create a standardized benchmarking methodology with accepted and curated applications and datasets, consensus system configurations, and metrics for how to measure the goodness of these systems. And finally, we would like to build an XR systems research and development community that can work together to move this field forward. So now let us do a deeper dive into ELLIXR. Here is an overview. ELLIXR consists of three interacting pipelines that are commonly present in any generic XR system. The perception pipeline, which determines where the user is and what the world around them looks like. The visual pipeline, this generates the pixels that are displayed to the user based on their perspective or pose. And the audio pipeline, which plays spatial audio, also based on the user's pose. So the various the various components of these three pipelines interact with each other through the ELLIXR communication interface and runtime. Right, and so ELLIXR, so this is an entire system, and it is able to run XR applications written to the OpenXR interface. And we do this by leveraging Monado, which is an open source implementation of the OpenXR interface. Today, all of the ELLIXR components are in software designed to run on a mobile device. In the future, we also plan to include support for hardware acceleration of these components. So next, let us look at each part of ELLIXR in more detail. We start with the perception pipeline, which includes interfaces to the sensors, such as cameras and an IMU, to provide the input to the rest of the system. The next component is visual inertial odometry, or VIO, which provides the position and head orientation or pose of the user. This is critical, of course, to any XR system to provide the right pose. VIO works, though, at camera frame rate, which is relatively slow and too slow, just to be the only producer of the pose in the system. So in addition, we have the IMU integrator component, which interfaces with the IMU and the VIO to provide higher frequency pose estimates. The next critical component for determining the pose is the pose predictor, which extrapolates the pose from the IMU integrator to future timestamps for purposes that I will explain soon. ELLIXR also has a scene reconstruction component, which uses RGB depth camera to build a dense 3D map of the world. And finally, in this pipeline, we also provide eye tracking to determine where the user is looking. In the visual pipeline, the first component is asynchronous projection, which is critical to address the motion to photon latency. The application takes the user's pose to render a frame from the user's perspective. However, the user's pose may change between the rendering start and the finish. So reprojection obtains a fresh pose to update the rendered frame to the new perspective. It also uses pose prediction to predict the pose when the frame will actually be displayed, and reprojects the frame based on this final predicted pose. The next component corrects for distortion due to the optics of the curved lenses. And this in ELLIXR is integrated with a reprojection component. And finally, ELLIXR supports computational holography to deal with the vergence accommodation conflict problem that can result in fatigue caused due to current displays with single focal planes. So this component enables displays with multiple focal planes and computes a per pixel phase shift for such a display. The audio pipeline consists of a spatial encoder which encodes multiple sound sources into a single high-order ambisonics virtual sound field, which can be easily manipulated for playback based on the user's pose. The playback component obtains the user's current pose and accordingly rotates and zooms the provided sound field. It also performs binauralization to account for the user's ear, head, and nose. So ELLIXR is not just a set of components, right? But it's a complete system with a runtime that orchestrates the system's data flow. So let us see the XR system data flow. We start here with the IMU that runs at a high frequency and produces a pose that works in concert with the camera, which runs at a lower frequency. So the camera and the IMU both feed into the VIO component, which runs at the frequency of the camera. Next, we have the high-frequency IMU integrator, which takes the pose from the VIO and the IMU to generate an integrated high-frequency and accurate pose. Eye tracking determines where the user is looking. And then we also have scene reconstruction, which uses the camera input and runs at a much slower frequency than all of the other components. The application takes input from eye tracking, from the IMU integrator, and from scene reconstruction to render a frame that it then submits to the reprojection component, which does the reprojection and submits the frame to the hologram. Meanwhile, audio encoding performs its recording, and audio playback uses the pose from the IMU integrator to play back whatever audio is appropriate for the application. So you can see that this is a fairly complex system with different components running at different frequencies, with multiple interacting pipelines, and synchronous and asynchronous dependencies, so soft or hard dependencies, and keeping track of multiple and balancing multiple quality of experience metrics. The ELLIXR runtime deals with all of this. So we've designed the ELLIXR runtime to be modular and flexible to enable a variety of research and development projects. ELLIXR components are plugins that are separately compiled and dynamically loaded. We can easily add new components and swap new implementations for a given component. The runtime is also it's also very efficient and provides a flexible and efficient communication interface. So each component in this runtime specifies event streams to publish and subscribe. Each component provides its synchronous or asynchronous consumers, and the runtime uses shared memory, providing a copy-free and efficient implementation. So overall, we have an end-to-end system that balances flexibility with efficiency. For applications, we can write XR applications directly to ELLIXR. And in addition, we can also, ELLIXR also supports OpenXR applications. So as I said earlier, we are fortunate and are thankful to the Monado group for their awesome implementation of the OpenXR interface, which we leverage for ELLIXR. The experiments you will see today are run on the OpenXR compliant Godot game engine, which is an open source game engine with many applications. Today, ELLIXR runs on Linux, and our support for popular engines such as Unity and Unreal is following their OpenXR Linux support as it becomes available. We are in the process of integrating Unreal or porting Unreal to ELLIXR as we speak. ELLIXR also supports various end-to-end quality metrics, such as the motion to photon latency, which is the time from the head motion to the display. Currently, we don't measure the actual display latency, but we measure the rest of it. For image quality, We support SSIM and FLIP, which are state-of-the-art metrics, and the system is extensible to support other metrics as well. For pose, we support average trajectory error and relative pose error, and we also provide extensive telemetry with standard metrics such as frame rates, missed frames, time distributions, power, etc. And finally, here is a summary of all the components that ELLIXR supports today in the perception, visual, and audio pipelines. For several of these, we support multiple algorithms and implementations. So for example, for VIO, we support two separate ways of doing VIO, different ways of doing scene reconstruction, and these are increasing as we speak. We can configure and study ELLIXR with any appropriate subset of these using live or offline data sets for a variety of experiments and research. So next, I'm going to pass this on to Josefa to describe how we have used ELLIXR.
Thank you, Sarita. The ELLIXR testbed can be used for developing new components, benchmarking systems, and researching new ideas. This is made possible by the level of extensive information provided by the testbed, which gives users insights and ideas for optimizing their designs. In fact, we have already thoroughly benchmarked and analyzed ELLIXR. This table here shows the various system-level knobs that a user can set when configuring the testbed. Examples include the display resolution and frame rate, the speed of the IMU, and so on. The final values that we used for our benchmarking are shown here in the tune column. We use these values to provide the best possible user experience on a desktop machine. In terms of hardware, we used 3 different configurations, a high-end desktop machine, and 2 variations of the NVIDIA Jetson Xavier development board, a high-performance version with the clock speeds maximized, and a low-power version with reduced clock speeds in order to limit the power consumption. To drive the testbed, we used 4 different extended reality applications, ranging from high graphical intensity to low graphical intensity. First, we have the frame rate results. The graphs here are organized by the hardware platforms, desktop, Jetson HP, and Jetson LP. Within each set of graphs, we have further subdivisions based on the various pipelines. First, we have the camera part of the perception pipeline, then the IMU part of the perception pipeline, the visual pipeline, and the audio pipeline. Within each pipeline, we have subgraphs for the various components. For instance, the audio pipeline includes the playback component and the audio encoding component. And then within each component, we have 4 bars, which represent the 4 different applications that we use to drive the system. The y-axis of these graphs is capped at the maximum possible frame rate for that particular component. For instance, the maximum possible camera frame rate is 15 frames per second. That is why the y-axis is capped at 15 frames per second. Going through these graphs one by one, we first look at the desktop. And there are no surprises here. The desktop is a very powerful machine, and in most cases is able to meet the target frame rates. But the question is, what is the power cost of this performance? When we go from desktop to Jetson HP to Jetson LP, we realize that by the time we arrive at Jetson LP, audio is the only component that is running at the target frame rate. All other components are unable to meet their deadlines. So these results show that there is a significant gap in performance when it comes to comparing modern embedded systems and what is required of them to run futuristic XR applications and systems. Furthermore, this gap is expected to increase as time goes on because displays will increase in resolution, frame rate, and field of view. The number of components will increase, and so will the complexity of the individual components. The dual of the frame rate is the time per frame. We have the same layout of the graphs, organized in exactly the same way, but now the y-axis, instead of showing the frame rate, shows the time per frame. Additionally, in the graphs, we have a horizontal red line, which shows the deadline for that particular component. For instance, if the display is running at 120 Hz, that means the application has 8.3 milliseconds to finish rendering a particular frame. Again, the trend is the same as before, which is that the desktop is able to meet most deadlines, whereas Jetson LP is not. Furthermore, when we get to Jetson LP, the variation in the execution time also increases. This is best captured by a time series graph of execution time per frame of the individual components. We show two graphs here. The one on top shows the execution time per frame for the application and VIO. The one at the bottom shows the execution time per frame for all of the other components. Both VIO and the application are input dependent, and therefore a certain level of variability in execution time is expected. However, the other components are not input dependent. And what that means is that when you run them in isolation, they actually have extremely consistent and stable execution times. However, that is not what we see in the graph here on the bottom. What we see is significant variability in the execution times of these components. And the reason behind that is both resource contention and scheduling. And therefore, when designing these systems, the designers must be cognizant of input dependence, scheduling, and resource contention. Next, we take a look at where the CPU cycles are spent among the different components. This graph here is divided by the hardware platforms, desktop, Jetson HP, and Jetson LP. Within each platform, we have 4 bars for the 4 different applications, and each bar is divided into where the time was spent, where the CPU cycles were spent in terms of the different components. At first glance, we see that both the application and VIO combined dominate the CPU cycles. And therefore, our gut reaction is that if we were to optimize these 2 particular components, we would be optimizing the entire system. However, we must not forget that there are other components such as reprojection and the IMU integrator, which take very little time, but at the same time are also critical for the final quality of experience. And therefore, it is not sufficient to just look at performance to decide which components to optimize. We must look at both performance and quality and look at all of the components together in order to optimize the final system. Moving on to power, we first look at total power consumption, which is as expected. The desktop consumes somewhere between 100 and 200 watts, depending upon the application that is being run. Jetson HP has a significantly lower power consumption, and by the time we get to Jetson LP, we're consuming somewhere between 7 and 8 watts, depending upon the application. The more interesting result, however, is when we look at the breakdown of power within each of these platforms. Specifically, when we look at Jetson LP, we see that CPU, GPU, and main memory constitute only about 50% of the total power consumption. The other 50% comes from SoC power, which includes various microcontrollers, and system power, which includes disk, driving the display, USB, and other I/O, and so on and so forth. Therefore, when optimizing the power in these future extended reality systems, we cannot just be looking at CPU, GPU, or just compute units more generally. Instead, we must look at the system level power components as well, such as display and I/O. Moving on from performance and power to quality, we first look at the motion to photon latency. These numbers here do not include the display latency, they only include the time up till frame submission. The trend is as expected. The desktop has very low motion to photon latency and also has low variability in the motion to photon latency. And as we go towards SNLP, the motion to photon latency increases, and so does the variability in it. This is better captured by a time series graph. First, let's take a look at a VR application such as Sponza. The horizontal red line here shows the target motion to photon latency, which is 20 milliseconds. We have 3 separate time series, one for Jetson LP, one for Jetson HP, and one for desktop. And we can see that desktop is comfortably within the 20 millisecond deadline, even accounting for the variations. Jetson LP and HP, however, do have significant fluctuations in the motion to photon latency. Even though the average might be below 20 milliseconds, there are frequent spikes that go above 20 milliseconds, and these are actually noticeable when using the system. When we look at an AR application, such as AR Demo, the requirements are even tighter because in augmented reality, the motion to photon latency has to be 5 milliseconds or less to provide a good user experience. And here we see that even the desktop has a tough time providing a good user experience. And by the time you get to Jetson, it becomes quite a bit unpleasant. The other quality metric that we looked at was image quality. This is captured by two different metrics, SSIM and FLIP. SSIM is a traditional image quality metric. FLIP is a metric designed by NVIDIA based on perception science and released recently that is more tailored towards the use case of extended reality. We also look at pose error, where it is captured by the degree error for rotation and the error in meters for the position. The trend again is as expected. The desktop has the highest quality and the lowest pose error, whereas Jetson LP has the lowest quality and the highest pose error. The interesting thing, however, is the rotational error in the pose on Jetson LP. It is 138 degrees. What this means is that the tracking does not reflect the actual movements of the user. Now, if we go back and look at the performance of the tracking components on Jetson LP, we see that they were actually really close to the target frame rate. The target frame rate was 15 frames per second, and the tracking was running at approximately 14.5 frames per second. If we were to look at just the performance results, we might say that VIO is running just fine on Jetson LP and perhaps does not need that much of an optimization. However, it is only by looking at the final quality results that we figure out that there is in fact some number of frame drops happening that result in irrecoverable errors. And therefore, we cannot just look at the metrics of a particular component. Instead, we must consider the end-to-end QoE when designing these systems. Second, with such a high pose error, we would have expected the image quality metrics to be even lower. 0.68 for SSIM and 0.65 for FLIP are not particularly high, but they're not as low as, say, 0.1 or 0.2 or even lower, given that the rotational pose error is extremely high. And therefore, these results also motivate the need for better QoE metrics for extended reality. We have looked at several different results at the system level, and these have very interesting implications for system designers. We saw that there is a gap in power, performance, and quality, which motivates specializing the hardware, the software, and in fact, the entire system. We saw that there's no single component that dominates all three power, performance, and quality metrics, and therefore we must look at the entire system together when optimizing. We also saw that the compute and DRAM power only accounts for 50% of total power on Jetson LP, and therefore, when optimizing for system power, we must look at system components such as display and I/O. We also saw that there's significant variability in the execution time of components for various reasons, and that motivates partitioning, allocation, and scheduling of system resources in an efficient manner. We also saw that per component metrics do not capture the final quality of experience, and therefore we must look at the end-to-end QoE and not per component QoE when designing these systems. Moving from system-level results to the individual components, we find similar interesting insights. First, we look at the microarchitectural behavior of the various components. We see that the components differ not only in terms of instructions per cycle, but also in terms of the number of cycles that they spend doing useful work or being stalled on the front end or the back end or on bad speculation. That is to say that there is significant microarchitectural diversity amongst the different components. These graphs here show the number of tasks within each component, and it can be seen that there is a significant number of tasks across the board. Furthermore, there's no single task that dominates a particular component. We count 27 different tasks here, and we expect this to increase as we get more components. Furthermore, each task itself consists of several subtasks, so there's a variety of compute and memory primitives that can be found within the ELLIXR testbed. We already looked at several interesting implications based on system-level results. There are also similar implications based on the per-component results. First, given the abundance of tasks and the fact that no single task dominates, means that manually figuring out what to accelerate and then designing that particular accelerator might not actually be feasible. And that motivates the need for designing automated techniques for determining what to accelerate and then actually generating the accelerator. It might also be impractical to build a unique accelerator for every single task due to constraints of either area or engineering costs, and therefore we must reason about building shared hardware. The final SoC must provide flexible on-chip memory and communication interfaces to accommodate the varied compute and memory primitives found within the different components. And given that the components are still in flux, the algorithms are still being designed, a certain level of programmability will be required in the hardware. And finally, given that the different algorithms have different trade-offs in terms of quality, power, and performance, we would require an end-to-end QoE-driven methodology for coming up with approximation techniques. All of these results suggest that ELLIXR is a rich playground for performing XR systems research. In fact, we are performing much of this research already in our ELLIXR group. We are looking at designing accelerators and memory systems for XR, looking at compiling to heterogeneous hardware, coming up with new QoE metrics, and then using these metrics for performing scheduling, and looking at partitioning work between sensors, the device, the edge, and cloud servers for computation offload, for streaming, for multi-party XR. In terms of the testbed, we are looking at developing new components, such as spatial reprojection and hand tracking. We have already begun work in integrating the Northstar augmented reality headset into the ELLIXR ecosystem. We are also broadening our hardware and software support. And of course, we are also looking into incorporating the findings from our research projects back into the testbed. Finally, on the consortium front, we have set up various working groups on different topics. And as was mentioned before, our goal is to build a reference open source testbed and benchmarking methodology, and also to build a community of XR system researchers and developers. To recap, ELLIXR, the Illinois Extended Reality Testbed, is the first open source full system testbed for extended reality that provides a rich space for performing XR systems research and aims to democratize XR systems research, development, and benchmarking. To find out more about ELLIXR, please visit illixr.org or contact us at illixr@cs.illinois.edu. Finally, ELLIXR would not be possible without the amazing team ELLIXR, which consists of both graduate and undergraduate students. ELLIXR would also not be possible without consultations with both academic and industry collaborators and advisors. Thank you so much for your time.